Hey, welcome everyone. Chapter 3, Addressing on the Networks. Now, what we're going to really be discussing here in this chapter is the different type of network addresses that we have on our networks, on our computers, and how our networks use them to be able to communicate to the millions and millions and millions of other devices out on the networks, out on the internet, internally on our own enterprise networks, in our homes. All of our devices have the ability to talk to each other, and it is not magic. So we're going to look at the different types of addressing that we either put on our network cards or are even part of our network cards. And what we really hope to get out of all of this, we're going to show you how you can find the MAC address on your computer. The MAC address is a hexadecimal address that is burned into every single network card out there. We're going to look at ways to set up the TCP/IP settings on your computer, whether they be received from a domain network controller or your home router, or you plug them in yourself. And we're going to look at the purpose of what a port is, what a socket is, and identify, a lot of the common ports and protocols that we have on our devices. We're also going to be able to look at the what are domain names like Google.com, hack.edu, Microsoft.com. What's a top level domain? What's a secondary level domain? We're going to look at how these names and numbers are used, and where we get them from. Like, I don't know the IP address of Microsoft.com. My computer doesn't know the address of Microsoft.com. So what is occurring? Because when we type in our address www.microsoft.com, something has to occur because computers don't know names, computers know numbers. We're also going to look at some of the command line tools that are used at the command prompt to troubleshoot our networks. So if we go all the way back and we look at chapter 1, you learn that the OSI model is used to describe pretty much everything that we do in computer networking. It's set up so that the modules of the OSI reference model, for those of you who don't remember, it's, please do not throw sausage pizza away. P for physical, D for data link, N for networking, T for transport, S for session, P for presentation, and A for application. And at each individual layer, we've got different things that we got to be able to troubleshoot. You saw that as we work our way up or down through the 7 layers of the OSI reference model, there's different things that are happening to our mail as it goes on through. In chapter 2, we looked at the different things in the network's infrastructure and looked at the documentation and maintaining and troubleshooting a network. You designed a network in CNT 120. You designed the racks. You set up switches, stuff like that. In chapter 1, we also looked and we talked about like different addressing methods at the physical and data link layer, and then how those addresses work their way up the OSI reference model. If we go back to the data link layer, the layer in which our switches actually operate, switches themselves utilize the MAC address. The MAC address is that address that is burned into every single network interface card. It's a 48-bit hexadecimal address. It's represented in groups of what we call hexadecimal numbers, typically separated by colons. And I will say typically because those sometimes when we look at them, they'll be separated by a hyphen. Okay. It's also called your physical address. So your MAC address, your data link layer address, your physical address, and you will also hear it called at times the Ethernet address. A lot of people get that confused. Then we have our network layer addressing. Now there's two types of network layer addressing. Now those are our IPv4 addresses, which is a 32-bit dotted decimal address. So for example, you might have an address at home on your computer. If you were to open up a command prompt right now and you would do type in ipconfig, all one word, all lowercase, you might see it says 192.168.1.52, and then it'll have a subnet mask paired with it. Please remember that every network address, every 32-bit IP address must be paired with a subnet mask. And we'll get into that later on when we start actually working with subnetting, which is going to be a very detailed chapter that we're going to have to do together. And I think what I'm going to do to really help us get through that, I have a lot of things on video and I have everything already set up, but I thought maybe I might set up a GoPro and do one on a giant whiteboard to kind of teach you guys how to do things. But we'll see what we have prepared, and we'll see if you guys are struggling or not. But the network layer IP address is a 32-bit dotted decimal address represented as decimal numbers separated by a period, dotted decimal. Then you have the IPv6 addresses. It's a 128-bit address, and it's 8 blocks of hexadecimal numbers. This was set up because we were running out of IP addresses. So we came up with another solution. It is a much more efficient way to network versus the IPv4 addressing. For some reason, people just aren't grabbing hold of it. It's actually easier to set up. We don't have to subnet it. I think what people don't like about it is it's just a lot more numbers to try to remember. 192.168.1.1 is a lot easier to remember than 2001:0002 ABCD 124C. It's just too much. And then we have something called transport layer port numbers. Now, what we got to remember about a port number is that a port number is used to keep track of the applications that are being used. So for example, my IP address might be 192.168.1.56, but I'm sending some email right now. So 192.168.1.56:25, because 25 is the simple mail network protocol identified by a number, 25. So that's how those things are kept track. And then at the application layer, we have things called an Fqdn, which stands for Fully Qualified Domain Name Service. Now what that does is on my network, it keeps track of computer 1, computer 2, computer 3, computer 4. I'm not going to remember that computer 1 is 192.168.1.64, and that computer 2 is 192.168.1.53. Those numbers change. But it would be nice if the computer remembered that it was actually called computer 1, computer 2, or computer 3, or computer 4. So that's how that works. Like, I don't know the IP address of Microsoft, but the DNS servers know the IP address of Microsoft. Okay. Now, a fully qualified domain name, like say for in a classroom, might be computer1.cnt.hack.edu. That would be a fully qualified domain name. Now, so let's go back and we'll talk about our MAC addresses one more time here. It is a 48-bit hexadecimal address. As you can see, like right here, burned into the network card, is a unique number. There are not supposed to be two MAC addresses alike. I have heard stories that someone said they had a duplicate MAC address on their computers, and it was a mistake by the company. A MAC address can be spoofed to make them to give you two identical ones, but typically you're not supposed to see two identical MAC addresses. The first 24 numbers, okay, the first 24 bits of a MAC address are supposed to be unique to the manufacturer. And then the second 24 bits are supposed to be unique to the card. And this makes up your 48-bit MAC address. Now we have dynamic addressing and static addressing. So I can tell you right out of the gate that my server in my classroom is 192.168.100.8. It has been 192.168.100.8 for about 15 years. I set it up that way. Why I chose 8, I don't know. But the fact is, I statically assigned it, which means I permanently etched it into the system. I went into my TCP/IP settings and I set it to be that. Dynamic addressing guy's driving me nuts. Okay. Dynamic addressing is when it's set up automatically. So, for example, on my server, I have what's called a Dhcp server. Now, that means it's going to dynamically assign a unique address to different nodes in my network. So, if I have 500 computers in my network, I will have a pool of addresses set up that will go out. So, things like my printer, my servers, okay, they won't receive an address dynamically. They'll be statically assigned because I want those to always be the same. But the people who are logging on periodically on my network, I would like for them to get unique addresses. So I have those all set up dynamically. So I keep a pool of addresses for them. So they'll get an address when they log on, and then 8 hours later, when they're logged off, their address will go back into the pool. Okay, and we'll talk about DHCP in a little bit later on. The TCP/IP settings on my computer can be found in a number of different ways. The easiest way that I have found to get to the to those settings is to right-click the little network icon on the lower right corner of my taskbar by the clock, and choose Open Network and Sharing Center, and then I'll go to my settings that way. Now we'll notice that we always have an IP address, and I mentioned that it's always going to be paired with a subnet mask. A subnet mask is used by the router to identify which network your computer belongs to. Then I'll have a gateway, and the important thing to remember about what a gateway is a gateway is a node on my network, typically my router, which allows me to get out of my network. It allows me to leave the network. That's what a gateway is. So and it's important because there are certain addresses that we have on our networks that don't work on the outside world. So the address that say I got from Verizon, or the address that I got from CenturyLink, or the address that I got from Comcast, okay, for my router, that address works on the outside world. The inside address, okay, if I'm running a Comcast network, it might be a 10.1.10. something. That address doesn't work on the outside world, so I have to translate that address into the public address. Maybe it's 50.42.32.16. I don't know. That 50.42. whatever, that address is my gateway. That address is how I leave. Now, on my Comcast network, my 10. network can only talk to my 10. numbers. So my address might be 10.1.10.1. That might be my gateway address. That is the address that I use to talk to the device that lets me escape my network and go to the outside world and get to the internet. I also have a DNS server out there. Now this is a node or a device that's whole job is to translate the name of a node to an IP address. See, routers and computers, they don't know names. They don't care about names. They know numbers. So there's a node out there that knows where the website is for hack.edu, that knows the website of dcts.org, that knows the website of microsoft.com, that knows the website of amazon.com. It knows the numbers between those two, and that's called a DNS server. Now, if we want to find out what our address is, it's real simple. Okay, all I have to do is go to a command prompt and type ipconfig, just like that. And as you can see, that I have a number of different addresses. In my wireless LAN adapter, my address is 192.168.100.57. I typed in ipconfig. If I'm on a Linux machine, I don't type in ipconfig, I type ifconfig. That's easy enough. As I mentioned earlier, the Ipv4 address is a 32-bit dotted decimal address. Those addresses are broken into 4 groups. Okay, these are our decimal numbers. 72 dot, see, dotted decimal. Okay, so when you're talking to IT people, I don't want anyone to say 72 period 56 period 105 period 12 period. It's 72.56.105.12. The numbers only range from 0 to 255, which is how we count up to 8 bits. Okay? Some IP addresses are reserved and cannot be used. For example, the 10 dot addresses are private. The 172.16 all the way to 131 are private. The 192.168.0.0 to 192.168.255.255. These are all private addresses. These are what we normally see inside of our networks. Okay, we have 5 different classes of networks: A, B, C, D, and E. A, B, and C are what we use. You and I are using to connect to the real world. Okay, D, okay, is for multicasting and multi-groups. Okay, and then E is for experimental use. Okay, these addresses here begin with 223 or 224. Sorry, 224. If we were to give an idea of why we ran out of addresses, if you figure there's 7 billion people on the planet, okay, if we were to say, okay, I've got 16 million addresses on 126 of these networks, I got 65,000 on 16,000 of these networks, and I have 254 addresses on 2 million of these networks. That's just not enough addresses if we are taking into consideration the number of IP addresses you yourself are using right now. Now think about that. How many addresses are you using? Well, you might have a Fitbit or a smartwatch, right? Or both. You've got a phone. You've got a laptop. You've got a tablet. You've got a Switch. You've got a Wii. You've got an Xbox. You've got a PlayStation. Then you take a lot of the other things into consideration that you may have that you probably didn't realize you were using that are using up IP addresses, like your smart TVs, your Roku devices, your smart home, your light bulbs, if you have a smart home. Okay, all those, your Google Nest, your Amazon, your Echo Dots, okay, all those are using up IP addresses. So it's pretty easy to understand why we all ran out of these addresses. As I mentioned earlier, the class D and E are not available for general use. D begins at 224 and goes all the way to 239. It's used for multicasting. To get a good grasp of what you think multicasting might be, multicasting is used when we have multiple computers or nodes that are going to be communicating with each other in a group-like session. So another easy way to think about it is, think about when you're playing Xbox Live and you're playing Call of Duty or some other multi-user game. Okay, you're using something similar to a multicasting event. Okay? Government and research is used to 240 to 254. Another address that you're currently not going to use is the 169.254. Now this is your API PA addresses. Some people call it a PIPA. I don't care what you want to call it. But it's an automatic private IP addressing. So if we think of it this way, your computer is designed to talk to your DHCP server or your router and say, hey, I want to get on the network, give me an address, and they gave you 192.168.1.57. It got it automatic. But what happens if the server that's supposed to give you that address isn't available? Your computer says, I'm supposed to have that address, please give me one. So it needs to have something in its place, and it's going to give you something that starts with 169.254.0. something, or 169.254.255. something, all the way up through those numbers. It's a lot of numbers. It's 64,000 numbers, 65,000 numbers. So your those numbers don't work on the internet, but your computer was told it had to have an address. So this range of numbers was automatically given so that you will have that number. Now, as I mentioned earlier, those numbers that we have, the 192.168 numbers, the 172.16 numbers, the 10 numbers, they don't work on the internet. So how is it that right now you're on the internet, you're watching this video? Well, we've taken your number and we've translated it. We've converted your number to the one lone public address. Now think about that. I'm in a building right now where there's 1,000 users. And I can take all their 1,000 IP addresses that are private, and I can push them all out, all of them out through the one public address very easily. That's network address translation. How do I keep track of all of them? Well, I use ports. So this guy's doing mail, this guy's doing web, this guy's doing YouTube, this guy's gaming. You know, everyone's doing something different, or they're doing something similar. So what I do is I'll take port numbers, either a dynamically created port number or a static port number for a particular application, and I'll append it, I'll attach it, I'll apply it to the end of their IP address, and that makes what's called a Windows socket. So if you can see here, I've taken that port address translation. So I got a 10.1.120:80. They're doing web. 80 is the port address for the World Wide Web. Okay, and I'm sending them out to 92.52.44.1, which is the web server, and I'll give this guy a dynamic address of :8000. Okay, and then the next guy, I'm going to give him 8001 because I have to be able to keep track of all these conversations that are occurring simultaneously. That is what port numbers are designed to help us do. Okay? There are a bunch of different ways that we can do this. I can do static NAT, okay, which means this address here is going to use this IP address to go out, or I can say this guy here, I have a pool of addresses and we're just going to share them with the group. That's dynamic NAT, okay? Which takes us then to IP version 6. Now we look at that address, 2001:000:000:000:000:000:9C5A:00CC. It's a lot to remember, and nobody wants to do that, so we get all confused and we say, we hate IPv6, but in the grand scheme of things, when we start doing subnetting, you're going to love IP version 6 because it's so much easier. I can look at that number and say, this number is a global address. This number right here works on the internet. I can look at that number and say, because it begins with 2001, it's a global address. It's huge, yes. We can make them smaller, okay? We can eliminate certain groups, okay? because it makes it easier. Right? We can eliminate preceding zeros. So we can make that 2001:0:B80, then actually get rid of that group of zeros right there and say : D3, :9C5A, :CC. I can make it easier, but what's really important is that this was developed so that we don't run out of IP addresses. Now, I know we're sitting back saying, well, we didn't think we were going to run out of IP addresses last time. We actually knew right away we were going to run out of IP addresses, but we used it anyway for some stupid reason. But this makes 360 undecillion. So it's 360 and then tack 36 more zeros on the end of it. That's how many IP addresses we have. So we should never run out. And if we do, let's hope it runs out before, or after my time expires, and I don't have to learn something new. So like I said, we can eliminate the preceding zeros to make it smaller. So as you see down here, 2001: we got rid of these preceding zero here, okay? And then we kept those guys together. That's one way to do it. It's not the way I would have done it, okay? I would have done it this way, okay? Now, in this one here, they could have also eliminated these 3 zeros and just put 1 0 in. The : can only be used one time, so you use it to get the most benefit. So I was able to eliminate the 10 zeros that were right here. See, 4, 4, and then those 2, so those 10. I eliminated those 10 with just those 2. If I used the : here, I got rid of those 4, but then I had to keep these. So I could have gone 0, : there. So this one here is the fuse number 0, so yeah, that's the preferred method. And we'll talk about that again when we get into the higher end numbering. Okay, there's different words we want to like vocab that we need to get a hold of here. One of them in IPv6 is a link. Okay, now the local link. See, when we look at our IP addressing, if we do an IP config, you're always going to have 2 IPv6 addresses. One is the IPv6 address that we use to talk to all of our devices inside of our network, and one that we use to talk to devices outside of our network. So if you ask yourself, well, this is supposed to be easier, why do I have to have 2 addresses? Well, if you're going to be talking to everybody in the outside world, do you really want them to have a chance to talk to your inside network? Do you really want that guy, anyone to be inside your network? No. So we keep a private set of numbers inside, and we keep a public one on the outside that talks to your inside numbers. Okay. Dual stacked is a term used when you're using IPv4 and IPv6, because not everybody's running IPv6 yet. And if we're going to use IPv6, okay, over an IPv4 network, well, we have to find a way to package that data and send it through the IPv4 tunnel until we can reach an IPv6 network, and that's called tunneling itself. And if we were to break down our numbers, since it is 128 bits, if we take the first 64 bits of our network and we split it into 2, the first 64 bits is going to be the network number. The second 64 bits is going to be your MAC address. It identifies your node. So the interface ID is the second 64 bits, the second half of your IPv6 address. That, folks, is your ID, your interface ID. Now, 2 or more nodes that are on the same link, we just call them neighbors. It's easy enough, right? A unicast address is an address that just goes to one individual. Global unicast is an address that is specific to another node on the internet. It can be routable. It's routed. If it goes across a router and out to the World Wide Web, it's routed. Your link local is the address that is specific on your individual network. A multicast address, okay, addresses that go to multiple individual or multiple nodes on a network, okay. And Anycast can go to identifies multiple destinations with packets delivered to the closest addresses. And there's just an example, and they're all pretty similar.